everyone. We are in problem 3 of lesson 3. In this problem we have a single phase transformer with apparent power of 125 kV amps, voltage in the primary of 3000 volts and in the secondary of 380 volts and a frequency of 50 Hz. In this power transformer we have performed an open circuit test in the primary circuit and a short circuit test in the secondary circuit. The first is the components of the no-load current in the open circuit test. As you know, the components of the no-load current are the current of iron losses and the magnetizing current. So we need to obtain both of them. For obtaining the current of iron losses, we need first the resistance of iron losses. The resistance of iron losses is going to be the square of the voltage in the primary winding divided by the power measured in the open circuit test. So that is 3000 volts to the square divided by 1000 watts, which gives a value of 9000 ohms. Now that we have the resistance of iron losses, the current of iron losses can be obtained by applying the Ohm's law. That is, the voltage divided by the resistance of iron losses. Resistance, and we will get to, obviously, 0.333 amps. So here we have one of the components of the no-load current. Now, we need to obtain the magnetizing current. The magnetizing current here, if we represent the no-load current, this component is the current of iron losses, while this vertical component is the magnetizing current, and here we have the angle, okay? So the magnetizing current will be the square root of the square of the no-load current minus the square of the current of iron losses. So that the no-load current is the current that flows in the open circuit test. So there you will have this current to the square minus this other current. So the approximate result for the magnetizing current is this. The current of iron losses and the magnetizing current. So what is the angle now? The angle can be obtained as arctangent of the magnetizing current divided by the current of iron losses. That is 65.39 degrees. So these are the components and the angle of the no-load current. In question B, they ask the power of iron losses and the power of copper losses at full load. First of all, the power of iron losses is directly the power measured in the open circuit test in the primary winding. So that is 1000 watts. What about the power of copper losses at full load? The power of copper losses is defined as the power of a short circuit test at the nominal load. So there, here we have the short circuit test in the secondary winding, but that short circuit test is not performed at the nominal load. So what is the nominal load? The nominal load in the secondary winding is defined as the apparent power of the transformer divided by the voltage in the secondary winding, the rated voltage in the secondary winding. So the power of the transformer is 125 kVA, so this in voltamps, divided by the voltage in the secondary winding, which is 380 volts. That gives a nominal load of 328.95 amps. So this would be the nominal load in the secondary winding. As you know, the active power would be the square of the voltage divided by the resistance. If we apply here the Ohm's law, we will have the current multiplied by the resistance and to the square divided by the resistance. So that is the square of the current, the square of the resistance divided by the resistance. So we will have the square of the current multiplied by the resistance. So then we can write that the active power in the short circuit situation is the short circuit current to the square multiplied by the resistance of the circuit. In this case we are talking about the secondary circuit. And the power of copper losses at full load would be the current, in this case the nominal current, to the square multiplied by the resistance. And the resistance must be the same because we are in the same circuit. So if we divide these two equations, we will have that the short circuit power divided by the power of copper losses at full load will be the square of the short circuit current multiplied by the resistance and divided by the square of the nominal current multiplied by the resistance. If we simplify the resistance here, as we want to obtain the power of copper losses at full load, we will have the power of the short circuit test and here the square of the nominal load divided by the square of the short circuit current. Okay? So, what is the power of copper losses at full load? The active power of the short circuit test multiplied by the ratio of the nominal current divided by the short circuit current and to the square. So there you will have 901.73 watts. So this would be the power of copper losses at full load. In question C, they ask the efficiency of the transformer at full load when the power factor is 0.8 inductive and 0.8 capacitive. The expression for the efficiency at full load is, in this expression which gives the efficiency, C is going to be 1 because we are at full load. Sn is the nominal apparent power of the transformer. Cosine of the angle is the power factor. P0 is the power in the open circuit test in the primary. PCC is the power in the short circuit test, but both must be performed in the primary. So this is the value of P0, but this power of short circuit is going to coincide with the power of copper losses at full load that we have obtained in question B, okay? So 901.73 watts, because that should be referred to the primary winding. Let's introduce the values. Here, this is 125 decibels. The power factor here, okay, 125, the power factor. P0 was 1000 watts. C to the square, and here the short circuit power is the power of copper losses at full load, okay? So it doesn't matter if we have an inductive or capacitive power factor, because both have the same value, 0.8, and the same sign. Both cosines are positive, okay? So here, if we introduce the cosine of 0.8, the result is going to be the same, and the efficiency is 0.981 in both cases. So in the last question they asked the voltage in the secondary circuit when we have the primary circuit with the rated voltage at full load, and in both cases with a power factor of 0.8 inductive and capacity. This was the expression that relates the voltage in the primary and the voltage in the secondary, okay? So we have N, the voltage ratio, also called transformation ratio, is the ratio of the voltage in the primary and the voltage in the secondary. It is 7.895. So this is the transformation ratio. We also need the resistance and reactance in the short circuit test. For obtaining that, first we need to know the values of the short circuit current referred to the primary winding. So what is the short circuit current referred to the primary winding? It would be the short circuit current of the secondary winding divided by the transformation ratio. 300 amps, that was the short circuit current in the secondary winding, divided by this transformation ratio, which gives approximately 38 amps. Then we need to know what is the voltage for the short circuit test referred to the primary winding. So there you need to multiply the voltage of the secondary winding by the transformation ratio. So this is the transformation ratio, and the voltage of the short circuit test in the secondary winding is 10 volts. So here we will have 78.95 volts. Now that we have the current and the voltage of the short circuit test referred to the primary winding, we need to obtain the short circuit resistance referred to the primary winding. The resistance of the short circuit test referred to the primary winding would be the active power of the short circuit test in the primary winding divided by the short circuit current in the primary winding. So the power here, remember that the short circuit power doesn't change when we are in the secondary or primary winding. The power is the same, okay? So you have this power divided by the square of the current we have calculated before. So there you will have a resistance of the short circuit test of 0.519. Regarding to the reactance of the short circuit test, we need first to calculate the value of the reactive power. So the reactive power is the apparent power, which is the voltage multiplied by the current and to the square here, minus the active power to the square. Apparent power to the square minus active power to the square. So there we have, this voltage is 78.95. This current is 38 to the square. And this power is the same as in the secondary circuit. So there we will have reactive power is this in multi-amperes reactive. Now that we have this, the reactance would be the reactive power divided by the square of the current, 2.012 ohms. So now we have all the values that we needed. So now that we have the transformation ratio, the resistance of the short circuit test, and the reactance of the short circuit test, we also need I2 prime. I2 prime was the nominal current in the secondary circuit divided by the transformation ratio. So that gives a value for I2 prime 41.61 amps. So now you have all the values that you needed, so you can introduce them in this expression. So in this expression that you have now, you need to introduce the values for a power factor of 0.8 inductive. That means that the sine of the angle is 0.6 and both are positive. So if you introduce that, you will have that the voltage in the secondary winding is. And if you introduce a power factor of 0.8 capacitive, then the cosine of the angle is positive, but the sine of the angle is negative. Okay? So that gives a value of the voltage in the secondary. So with that, we have solved problem 3.